let's restart. I want to go faster? Can. Okay, so this is unit 4. Okay, so we have a module. Okay, this is module 8, unit 4, and then we will do unit testing. Dr. Iswan?
What do you say about unit testing?
We have module 4. This is
Okay.
module what? Module. This is module number, right?
Yeah,
Then under module you have units. So
yeah.
unit
Yes,
is
yes. Module
unit is
4.4.4.
yeah, unit is smallest testable unit. Unit is the
Yeah,
smallest testable item.
and testable in your exam as well.
Yeah. Okay. So we're talking about software engineering terms there. Okay. So let's say we are going to access the GPIO port, right? So actually you have done it. Now we go back and revisit, yes, and try to recall what you have done. So there are several ways that you can use to access the GPIO registers. And once you know how to access the GPIO, you can apply the same techniques for any IO port. And all you have to do is find out what are the addresses. Okay, so the first method to access the register is using a raw pointer. Okay, so what you do is you find out the exact address of the register and you write it down in C directly. For example, I want to access IDR and ODR. Okay, so looking at this table, okay, IDR is 400, 210, and ODR is 400, 214. Okay, so if you want to make it slightly readable, then you can use macro lah. Okay, maybe you can say define, but let's say this you just want to be cruel to yourself, right? You want to use pure numbers. So in C, you can just do this lah. val equal to star Einstein long star, and then you put there 0x 400 210. So you will read the data from the GPIO input data register into the variable val. And for writing, you reverse the order. Okay, you put the source of data on the right, but the address to send is GPIO ODR. So you will put there 400 214. Okay. So even though the data is only 16-bit, you still have to use a long pointer. Okay. So you can use the same method also for assembly language programming. So in the example down here, I loaded R0 with the base address. So R0 contains 400, 200, 200, 2 followed by 4 zeros. Okay. So this is the value in R0. So if I want to access IDR to load the data from input data register, so I do the load. So remember that this is the IDR address. Okay. So 400, 4002 followed by 4 zeros plus 10 hex will be calculated using this expression in the LDR instruction, and you will get the data. So for sending data to the output port, same trick, different address, different instruction, but same addressing mode. Okay, so okay lah, you can use this if you do it once in a while only, and you really want to check whether the address is correct, then go ahead. If you are slightly smarter, you will use header files. So in this method, you will put the addresses that you want to use. For example, GPIOA ODR. This should be A here. GPIOA IDR and ODR, and you write a macro like this, and put all the registers that you want in this particular file. But if you really want to get efficient, not say lazy, efficient, just download this file from this server here. I think I can plagiarize this. This is not really copyrighted. So maybe copy this and transfer to my own GitHub, something lah. And next time, no need to have this Evans spill there. But okay lah, just download from this guy and put it in your C code like this, include, and inside your C code, instead of the horrible looking C instruction there, you get a clean one. Okay, file equal GPIO A underscore IDR. This is a lot cleaner and a lot easier to read. So of course, the first method is just to show that you can do it, but it also shows you that it's ugly, that you should not do it. Here is a better way. Please do this. But of course, STM and all these big companies, they have better ideas. They say, don't do this. We have a more complex method. So now you use CMCs where you have all these constants defined in the CMCs header file. So all the registers are there. You don't need to type any of that. It's all there. When you go to Kyle, when you go to STMcube, the files are there. Just include it, and just have to make sure you got the right register. That's all. Okay. So for example, all the registers have a base address. Okay. So we have the base address. So this is the base address, and then after that we have the offset. Okay. So for example, we have GPIO A. Address itself is from here. Okay, this address should be the same lah, because it's 0. But B and A is differs only by 400 hex, and we can verify that from here. Okay. Remember this table. Okay, this table. Okay. So the first address for any block will be the base address. Okay, this is the base for A, and this is the base for B. And the base is also used for the mode register. So if you can look at the value itself, this one has a initial actually tail value of 0, and here the tail value is 400, and so on. Yes, so that is reflected in this. That's reflected in this include file. Okay, so you can see here, they just say, okay, take the peripheral base address at 400. That you will get the base for B, and then of course inside B, there's other specific registers. So they don't put it here. It's a separate define, but now we use the struct. Okay? So from the base address, you use the structure to access the individual registers. Okay, so we combine the base address. Okay, get this base address plus this struct, combine them, then only you can go to the register. So these two are combined to create pointer definitions. If you are really interested, you can of course read more about it in good C books. But for this, for the purpose of GPIO, just use. Okay, don't need to worry about it. Okay, so knowing that you want to access the output data register, there's two syntaxes. One is to use the proper C syntax. Okay, pointer there, and the pointer there, bracket there, and there's a dot. And there's a dot there because you are using a structure. So basically it's like this. Okay, GPIO A, and then you have a structure. Whenever you have a structure, you have a block of data. So the .odr will offset that to 14 or 10. That is ODR is 14. Okay, so 14 from the top is the ODR. IDR is just before that. Okay, so combine these two, you use this to send data out. And when you want to make it even cleaner, you use this arrow notation. So if you use the arrow notation, people have seen, people who know C will respect you lah, because you know how to use the pointer notation. Okay, so that is the third way. The third way, and there's 3A, 3B. Okay, remember that we have 3 methods so far. Okay, this is the messy way, cleaner way using a different header file, custom header file. Here we use CMC's header file, but 2 ways. So let's say this is method 3A, method 3B. Method 3B is the one that you can show off, okay, using the arrow. And then you can also use the method number 4 using the hull. Okay, you want to access the GPIO. Now you take advantage of the hardware abstraction layer from STM32. And the hull only exists for ST micro. Okay, don't try to use this technique on other companies' products. So hull makes it a lot easier to migrate between different STM32 controllers if needed. Okay, not between other companies' microcontrollers. So maybe from F4 you want to migrate up to F7, or you want to go down to Cortex M3. So most of the addresses may be changed, but you don't have to change anything. Okay, if you use this technique, you may have to change the addresses. Okay, these addresses may change if you switch to a different microprocessor series. But if you use HAL, port A will likely be there because it's always the first I/O port. The address may change. All you have to do is just recompile and make sure you go to the correct pin. Should be okay. Okay, so of course, not all is, people say not all is roses. Some disadvantage to HAL. Sometimes the code is inefficient. Sometimes, and then there's a lot of documentation. The documentation is like 1,000 pages, and some claim, okay, still work in progress. So this one may not be true, may be true, maybe not. Okay, so just be aware of that. Okay, so if you are using HAL, then there's some advantages there, because by doing that, you are locking yourself to an ecosystem from ST, just like when you buy Apple, you are locked to iMac and Apple Watch. So here, when you use this HAL, you are locked to products from STM. But let's say you are from a different product series, maybe from Novoton, which we used a few years ago, or from Atmel. So they will most probably use this kind of libraries where they are lower. Okay, so higher means less detail that you have to know. So if you look at the libraries that are provided by STM, they go much higher. So you don't get to see the details as much or you don't need to know the details as much if you use the libraries from STM. Okay, so if you use HAL, then you will need to link with your own code. Okay, so if you're using Kyle, for example, Kyle will generate the application code. So this part here, and then some of the HAL drivers will also be added in the folders like that. So you have to know where your drivers are, where your files are, and where are the files from HAL. But I think you have seen it when you did your Blinky, that your application code most of the time doesn't have to be changed if you switch any configuration using the cube configurator. So even though it looks complex, but if you know where your codes are, so everything should be okay. So now the method number 4, Blinky using HAL. We are trying to write data to an output port completely using HAL. So if you look at the code generated by STM32 and you remove all the junk, you remove all the comments, it all comes up to maybe like 10 lines only. Okay, so you have HAL init to initialize the HAL system, configure the clock, and then configure the GPIO. Then you are all ready to go. So to link the LED on the board, set it, okay, turn it on, delay for 200 millisecond, and then reset and delay, and then keep on looping. So if you look at this code, you can see there's too much code. Okay, so it depends on some people lah. It depends on the person. So this is the one of the disadvantage of using abstraction layer. It's that you have to type in more. Maybe here you just put, maybe this value is just number 0 and this is number 1. Okay, if you replace this with 0, it still works. If you replace this one, maybe it still works. But when you're using an abstraction library like that, you do have to key in more because it's supposed to be self-documenting. So you look at the code, you know what it's doing. So you know that you are setting a pin at the GPIO, and you know which pin, instead of like, okay, this one. Okay, do you know what it's doing? You do not know. Okay, no idea. Or this one, you don't know what this particular instruction is doing. But if you use this, okay, I'm trying to set pin 5 at the GPIO. All right, summary of the methods. You can control the GPIO using assembly, and we are able to use this. The shift operator works in assembly also. And then we can use C method number 1, the ugly method. We can use C method number 2 using slightly cleaner method, where you replace the number with a label. And if you're smart about it, you can delete this typecasting in front. Okay, and then you can use method 3A, 3B, but here is I renumbered it to 3 and 4, okay, and 5. Okay, so it depends on where you put your star actually. Okay, so method 2, 3, and 4 is actually the same. It's where you put the star. Okay, so probably if you compile these 3 lines, okay, method 2, 3, and 4, maybe the compiler still generate the same code, exactly the same code. We have method number 5, and then finally method number 6 is using HAL. Okay, only 323. Okay, let's go faster. Okay, so can go to the next unit. All right, so this is a general flowchart of using any port on the STM32. Okay, but the example is applied to GPIO. All right, so let's say I want to use the GPIO. I have to decide whether I want to use the built-in clock or I want to go faster. If I want to go faster, then I have to program the external clock. And then after that, does it have to do with PLL or not? If yes, then you have to program the PLL. And then you have to program the advanced buses. So this part, the dash line, is the one that is done by the STM32 configurator. And then we need to enable the GPIO clock to make GPIO work for us. And then we have to choose whether we want to have an alternate function. Okay, so if we don't want to use the GPIO, but we want to use a specialist peripheral, we have to enable the other clocks. So that means you have to go to the clock register go there and enable the clock. And then you have to configure the components separately. If you don't want to do that, just go ahead, go down, configure the GPIO, and possibly also program the interrupts and the NVIC. So the GPIO can interrupt the processor, but we skip it here and we don't show in this module how to use the GPIO with the interrupt. Okay, so the first thing is to program to enable the clock. Okay, this one. So at this particular address or at this particular register, there are many bits, but only one bit is important for using GPIO A. So it is the last bit. So by default, those bits are all 0. And if you want to use GPIO A, GPIO port A, you turn on the last bit. So just give this command. Okay. Then you can use the GPIO port. Otherwise, it won't work. And then you have to tell the GPIO what are the directions of each of the pins. Okay, so by default, they are input. By default, all the pins are input. But let's say I want to make only pin 5. Remember that for the blinky is pin 5. Okay, here we already output to pin 5, but you have to tell this register that pin 5 is output. Okay, this is PA, sorry. Okay, we have port A, and then we have pin 5. And we want to make this an output. So we don't care about the rest. We don't need to change. So we go here and find which pin, which bits control pin 5. So it is this one. So there's number 5 there. And to make it an output, you have to put 0, 1 here. So you put 0, 1 here. So what you need to do is actually, if you want to do it manually, you have to do it this way. GPIO A mode register. Okay, assuming we are using CMCs. So just use these labels. Now we have to turn on that bit. So just turn on that bit. That is bit number 10. So do this 1, left shift 10. Okay, there you go. So this will enable port A5 to become an output. Otherwise, it stays input. Okay, and then of course there's, because there's more than one bit there. Okay, the other functions are alternate function and analog mode. Okay, and then this is the data register that you use to send data out. As we know, only 16 bits are usable. So to send data out to pin 5, just send 1 here. So as we have seen, we can do it this way: GPIO A, arrow, ODR, set pin number 5. So 1, F shift 5. So you will turn on your LED on the nuclear board. Okay, so this is the minimal blinky. Minimum, that means the fewest lines that you can get by. Okay, first, we create a delay loop to make it easy later. So actually, because of this function, the program becomes longer. If you really want to make it short, you can compress that and put them inside the main program and not having a function. Also can. But anyway, by default, the speed of the STM is 16 megahertz, and accordingly, 1 millisecond can be you can have 1 millisecond by looping 3,000 times. So here you create this subroutine where you multiply 3,195 times the required milliseconds, and load that into a register, which is categorized as volatile. So when you do volatile, the optimizer or the compiler cannot optimize it away, cannot remove it. So it needs to loop and wait until the counter becomes 0 before it gets out from this function. So that one taken care of. Okay, so in the test probably will not ask you to do this. This is already provided. So if you are asked to write a program to do a blinker or something, write only the bottom part. Okay, assume this one is ready to be used. So in the main program, enable the clock. Okay, done. Enable pin P5 as output, and then toggle PI5 okay, after a delay. So after every half second, it is toggled. So to do that, you use the exclusive OR function there. Okay. To read data, you use the IDR, which is located at offset 10 hex. And to read the switch, which is at a different address, right? I think this is PC on the Nucleo. Let's go back. I forgot lah. Have to better check this one. PC13. Okay, PC13. So there's some typos there. This will not work if you copy this. Yes, because I use A here, so it should be C. So first enable the clocks for port A and C. Wait a minute, I don't care. This is correct because I want to make it. This is still the LED, okay, not the switch. The switch for the switch you don't have to do anything. You just read the input. So read the switch, and this expression will check that bit. So if the value is not 0, you turn on the LED. If the value is 0, you turn off the LED. So basically it just mirrors what you do on the switch. Actually, it works reverse. Remember that the switch is active low. Okay, switch is active low. So if you press, the signal will be like this. Signal will be like this. So if you don't press, you have high. So from this, what I do is, if the switch is high, turn on the LED. That means the LED is on by default because the switch is high by default. And sometimes you may want to change the clock, so you change it, the O speed register, the output speed register. So this is in relation to the system clock. Okay, it's based on the system clock because it's not the master clock. And then what we do here is just to toggle the output as fast as possible. Okay, so this one, okay, you can see that it's complex, and there's a lot of funny numbers there. And normally we don't do this ourselves. We just let the cube configurator do this for us. Okay, an alternative way to control the register, the pin is using this register BSRR. You can set a bit or clear a bit. So let's say I want to set bit 5. I will go to here and bit S. I would send 1 there. And if I want to reset, I send data here. But the thing is, this whole thing is one long register, a 32-bit register. Okay, so you can do the blinky using BSR also. So you can see here the data that you send to turn on and off at different places. Okay, no question, huh? Everybody is sleeping already? All right. We are 20 more pages to holiday.
So everyone's sleeping, huh?
So they need the SEV signal, send event signal to wake up.
Wake up from event.
SEV, send event. Oh, then hopefully they turn on the signal lah, the WFE.
Can I ask
Otherwise, cannot.
page 45?
What's that?
Page 45.
Oh, well, fine. Okay. Right.
The last line is GPIOD, right? Or GPIOA?
Yeah. Correct. Yep. A lah. I copy this by hand. I didn't copy paste. I copy from a different book, but I type. So some errors.
Hi, Doctor.
Yeah.
Just now the page 45, we're going to
Yeah.
set the GPIO file, right? So why do you shift then?
Oh, it's because this one. You're not sending data out yet. You are just changing the mode of the pin. And by default, the pins, they are all input mode. Input like that lah. But you want this LED is connected here, so you have to change at least this one to become output. So to change pin 5 to output, you have to go to the bit that control pin 5.
Oh, okay.
So yeah. So these two bits control pin 0. Okay. So pin 0, this bit, pin 1, these two bits, pin 2, pin 3, pin 4, pin 5. So this is pin 5. Okay. So one pin but two bits to control. So if you look at the bit position, this is position 10. Okay, position 10. So you have to put 1 0 at this. You have to put 1 there lah. Okay, the rest they're all 0 because by default they're all zeros. These are the default values. And the reset state are 0 0. Okay.
Okay.
All right. So that's why it's number 10 lah, not 5. Right? Because this is mode register, not the data register. Okay, so again, we are still in the output interfacing. Just now we use simple LED. Now let's say we have something other than LED. So we do have to look at the port, what the port can do. So in digital circuits, signal lines should never be allowed to float. They must be high or low. Okay, so when floating, you can have problems. It's possible to have problems. Maybe no problem, but it's possible to have problems. So if you set output, you either connect the signal to VCC or ground, even if it's output, and you need to have a register. So in microcontroller, the work of the resistor is done by PMOS or NMOS transistors. And for the GPIO, there's two modes called push-pull and open collector. But the default is to push-pull because for the push-pull is the normal way gates are supposed to work lah. The output is either 0 or 1. And the other option is what's called the open drain. Open drain, it's not open collector. Open collector is for TTL, but here it's called open drain because this is the drain, gate, and source. So the drain here is open. So let's say this is your microcontroller. This is your MCU. The output is like that when you configure as open drain. So there's nothing to drive, no current going out, but only current coming in. So you can use this to connect LED reverse bias. So there's resistor there, LED here, and then you can connect like that. So if you turn on the gate, this will turn on and current can flow. Okay, but if you turn off the gate, no current can flow, so the LED will not turn on. So it's okay, but there's only one way to turn on the LED, which is by reverse biasing the diode. If you are using push pull, it's okay. You can also do it. You can still connect it that way. Okay, let's say you want to reverse bias, still possible. Okay, you can either do it this way. Alternatively, you can also connect this forward bias like that, go to ground. Okay, so when previously all microcontrollers, they only allow this one no, but the current trend is to use the bottom method lah, because the current sourcing is equally high. Okay, many older microcontrollers, like also many TTL legacy devices like 7447. Okay, there's this chip, right? The famous chip, the BCD to 7 segment decoder. The 7447 is a common anode, because reverse like that. But the 7448 is common cathode, goes forward like that. The current is not the same. This one is 20 milliamp, this one is 5 milliamp only. So if you want bright LED, you need to use 7447 reverse bias. But for STM32, the current coming in and current coming out is the same at 25 milliamps. It's actually even better than 7447. So you can use the bottom method if you want to use if you want to connect for you connect your LED, and this is active high. That means turn it on and sorry, 1 on, 0 high, which is more intuitive. If you use open drain, 1 is off. If you put 1 here, it's off. You put 0, then current can flow. But of course, here is reverse lah. You put 1 here, current can flow. But at the pin itself, okay, 0 is what makes the current flow. Okay, so to select whether you want to use push-pull or open drain, you use this register. So not sure why you would want to use open drain method anymore, because the current sourcing capability is quite high in the current crop of microcontrollers. Previously, maybe you would want to use this to have higher current. But if you look at the gate, maybe you can study the gate configuration, maybe slightly different current rating, I don't know. But if the same current rating, no point using the open drain method. Okay, so again, you can connect the LED forward bias or reverse bias, and most LED need about 10 to 20 milliamp to turn on the LED. So this two connection method goes back to whether you use forward bias or reverse bias. Okay, so I think everyone is settled. Okay, all right. So let's say you want to have a lot of LEDs and want to make it a light rider. You want to make a running light. So you can connect 8 LEDs like this. And this is the code. Okay, so you send this pattern. Okay, for example, here is 80. So you will turn on one LED at this position, and then you send after another pattern after some delay, where you move the position of the LED that is on, and you keep on doing that. But the pattern here actually makes the light go zigzag like that. Then to go right and left like that, not just one way. So that's why I put it in an array. If I were to do this circuit myself, okay, this is definitely copied from internet somewhere, right? If I were to build this circuit myself, I will not use, I will not put this resistor here, I will put it here, okay? I will have 8 LEDs immediately after the output. Okay, this is assuming I'm building my own PCB lah. Okay, and then I will put the resistor here, like that, because I can use an SIP resistor. Okay, let me find a picture for you. Okay, so you can actually use a resistor like this. So let's say I want 8 LEDs. I find a resistor network with 9 pins. So one is common like this. Okay, 2, 4, 6. This is 10 pins. This is 8 pins. So there's only 7 resistors, and this one has 9 resistors. If you want to really optimize your place, your circuit board area, find the one that is 9 pins. So only one pin is common to ground, and the other 8 will goes to the LED lah. So if you use that SIP, then the board space will be more compact. So that's what I will do. Of course, I have not counted the price lah. This method could be more expensive. So that depends. Okay, next we can connect the output ports to 7 segment. This is common knowledge, right? A lot of people have used this. You turn on the particular combination to get the digit that you want. Then you can choose either common anode or common cathode. And you can connect directly. Okay, you can connect directly like that. So basically, we are using forward wires like this. So this one this one looks like a common cathode, right? Common cathode type. Okay, so this looks like a common cathode type because the common is to the ground. Okay, so this one is 1 on, 0 off. So let's say we want to for exercise, you can maybe write C code to show decimal values, which is incremented 1 every second. So that means you go from 0, 1, 2, 3 up to 9, and then go back to 0. And if you want to show hexadecimal values, you can, because you are able to control all the 7 segments yourself. And this is not possible if you use external decoder like the 7447 chip. Okay, so if you use this chip, for example, 7447, the number is correct until 9, and after that, seemingly random patterns will be displayed. And again, if you are going to connect this, you need to calculate the resistor. So these are some calculations. I think for most cases, we just put the 220 around that. If it's too dim, you reduce. So I don't know about you. Don't put too high. For example, 470 ohm will be too high. This one will be too high and will be dim. Okay, but put something. So if you don't put anything, you will burn the LED very quickly. Or you can be very mathematical and very rigorous, calculate the current there, and calculate the exact resistance required. But no matter how you do it, you probably cannot get the exact resistor that you want, because maybe you cannot find 120 ohm resistor. So you still need to do an approximation because you have to choose the next and the closest resistor to the value that you calculate. All right, if you have a lot of segments to drive, then you can save some pins on the STM32 by putting the external decoder lah. So of course this is extra cost, but only 4 pins will be required. If you have if you're connecting directly for one digit, maybe okay lah. Okay, let's say I have 4 digits, then I need 7 times 4. So that's 28 pins directly from the STM32. So whether you have the pins or not, it's up to the application, or maybe you have used the pins for other purposes. So you may not be able to find 28 pins. So that's why you do need to use the 7-segment outside. Okay, 7-segment driver outside. Okay, so let's say I want to display 1, 2, 3, 4. Okay, 1, 2, 3, 4 here. I will send 1, 2, 3, 4. Okay, let me see. I want to calculate 1, 2, 3, 4 in binary quickly. Okay, so the number may be 1, 0, 0, 1, 1, 0, 1, 0, 0, 1, 0. This is 1, 2, 3, 4 in decimal, but this is in binary. But the displays here requires that you already split the number to 1, 2, 3, 4. So you do need to convert the numbers from binary, okay, from binary to BCD. So normally you have to do a simple routine. So just telling you lah. So last semester we asked this. Convert from binary to BCD. 0. Okay, nobody got it right. So BCD numbers are still important. Okay, so here we are sending data. Okay, so the conversion is not shown. And then if you have if you want to save pins, maybe you don't want to put, maybe you don't want to use 7-segment driver, and you don't want to use too many pins by driving directly, you can use multiplexing. So here, only one segment is on at one time. So let's say I want to display 1, 2, 3, I will display 1 first, and then I display 2, and I will display 3 at different times. And I toggle them very fast so that the user sees 1, 2, 3 on at the same time. But actually, only one segment is on at any one time. So normally the speed is you have to switch them reasonably fast, but not too fast. Maybe about 10 to 20 hertz. Okay, if you go too low, you'll see flickering. Okay, if you switch from digit to digit too slow, you will see flickering, because you can see the number 1 being turned off, then you can see the 2 turn on. You don't want it too slow. If you go too fast, like you switch from 1 to 3 too fast, the LED didn't have time to achieve maximum brightness. So this number is again empirical. You have to do experiments, and also depends on the kind of LED that you have. How fast is the rise time? If it's a very fast LED, then you can switch faster. Okay, so for 2 digits, it's like this. Okay, put the current driver outside. And then we are like a few more slides left before you can go. Okay, it's only 3:54, but I think you all are impatient. Layan sajalah. So let's finish this. Okay, less than 10 pages left. All right. Okay, so for input, the techniques are slightly different because now you have switches. So for switches, you need to have a pull up or pull down resistor to ensure logic value, a valid logic value. And you may need to have capacitors. So for one switch, like the one on your nuclear board, you can afford to put capacitors, but capacitors take space on the board. So you may not be able to do that all the time. So anyway, if you look at this diagram on the left here, if you open, let's say we connect the microcontroller here. Okay, So you open the, if you open switch, you will actually read 1 logic high. And if you close the switch, the capacitor will discharge and actually you will drain the current like that. Wait a minute. Yeah, this one will be 0 because this is shorted. So this is shorted. This is 0 ohms here. So you'll get 0 here. Okay, so you choose either one, whether you want to make it pull up or pull down. So this is a pull up method where open is VCC or high. Okay, open 1 and close is 0. Or you can use a pull down method. Open is 0, pressed or close is 1. So this one is maybe like more intuitive, at least to me lah. It depends on some people, and depends on who you are. Maybe you like it better this one, but I think this is more intuitive lah. You press it, you get 1. You don't press it, you get 0. But most of the diagrams that we see, if you look for diagrams, you will see pull up method. So to select whether you want to use pull up or pull down, you use the GPIO pull up, pull down register. Okay, PU is pull up, PD is pull down. So program it here and do this for every bit. So by default, no pull up, pull down, or you can use pull up or pull down. The combination 1-1 is not supposed to be used. So what the good thing about having this pull up, pull down is that it will enable the internal resistor inside the microcontroller so that you don't have to add your own pull up resistor outside. So you can save some cost. Okay, so like this diagram, we are not using the internal pull up. So this is like a waste lah. Okay, don't do this. Just by programming, you can eliminate the hardware cost. Okay, so this is how you read the switch from GPIO port C. This is port C lah. Then of course you have to enable the clock for port C. And second last slide, key bounds. Okay, so I have mentioned key bounds just now. So on your Nucleo, you have the RC. Okay, so of course that one no problem because there's only one switch, and also people who are first timers to use the Nucleo board don't know about the key bounds. So they press a button, they expect to have clean output. So of course the board already included the RC there. But if you are building your own system and you have to connect a lot of switches, the capacitor may cost a lot because there's so many switches that you have to connect. So you don't want to use any of the hardware approaches. Okay, so these are all hardware approaches. They require you to add things to the board, and they will involve cost and also board space. So what you do is you do software debounce. Okay, just read the pin. Okay, read the pin. Is it high? Okay, is it high? Okay, if it's high, just keep on waiting. If it's low, okay, that means if it's high, right? Okay, this is the pin. High, wait. 0, you delay. Okay, delay for 10 milliseconds. Normally 10 milliseconds is a good value. So what you do is the moment you detect a 0 there, you wait for 10 milliseconds, and then you read it again. So you check the pin again. If it's 0 again, then okay. So use the 0. Use the 0 bit. Or the value 0 lah. That means the key press is confirmed. confirm. Okay. Otherwise, first you press, you read it 0, and then when you check 10 milliseconds later, it is 1. So you have to go back there. So maybe this is a slow switch. So you read it again here at 10 milliseconds. Okay, first 0, then you read the second time is 1. So then you have to reset. So scan it, go through the top of the loop. So normally this method is enough, but if you are not careful, you set the delay too slow, okay? And then people who are using your system will need to press a long time before the press can be detected. So that's also not good. So the delay amount should be just right. Okay, I don't know about you, if you still have used roadside phones. Okay? No, now no more, right? There was one phone that I used maybe like 10 years ago. It needs you to press like 1 second for each button. Don't know why that has to be. So that was really annoying to me lah. So if you are doing your product, test it on the user, make sure the user feels comfortable using it. Don't be like that. Okay, Dr. Osman, let's close shop for this week. Dr. Osman is not here. All right, guys. Use the QR code from yesterday for the feedback.
So the QR code we shall scan through the UTM apps or like you just usual any scan.
If you are using iPhone, just use the photo, the camera. It will detect it as a QR code. I think on Android you use Facebook scanner or any other scanner lah, because it's routed to HTTP. It is just a URL actually, but you don't have to key in the URL. Okay, class dismissed. Have a good weekend. Enjoy the 1 hour leave home early today. Dr. Osman, you're still around?
Yeah, I was answering call from Sheikh Nasir just now. He's alone at the VCAT lab.
Why?
I think
What?
the others are discussing something outside. I don't know.
Okay.
All right.
Anyway,
Yeah. So I saw it's already at the 75th slide. So class is dismissed. You mentioned that in the chat.